Hey everyone, let's see, last time we introduced this idea of a multiplicative norm. So remember, a multiplicative norm, that's just a function from an integral domain to the integers, right, that has these two properties. So first of all, only 0 goes to 0, right? So n of a equals 0 if and only if a equals 0. And then the second property is this multiplicative property, n of ab equals n of a times n of b. And then what we did we had a theorem that tells us something about, or tells us that we can use norms to identify irreducible elements, and it goes like this. So if the absolute value of the norm of a equals 1 only when a is a unit, right? We show, well, first, the first part of that theorem tells us that units always go to plus or minus 1. So now if that's the only elements that go to plus or minus 1, so only when a is a unit, then it has the following property. If the absolute value of n is a prime, right, then a is irreducible. So this idea of multiplicative norm can, when this property holds, can be used to identify irreducibles. Now, so I need a definition for here. Sorry, I just spaced out for a second. So an integer n is square free if it is not divisible by the square of a prime. Right, so for example, well, of course, 1 is square free. It's not divisible by the square of a prime. 2 is square free. It's divisible by 2, 1 and 2, but not by the square of a prime. 4 is not square free, right, because it's divisible by 2 squared. And so, in general, if you write out the prime factorization, it's going to be square free if, when you write the prime factorization out, and we allow negative numbers here also, but when you write the prime factorization out, you don't see, it'll be plus or minus a product of distinct primes, right? There won't be any repeats. Okay, so with this definition now we can state the following theorem. So this is theorem 47.2. So let's let n in Z be square free, and n not equal to 1. Then the function n from Z bracket square root of n to Z, defined by n, capital N, of a plus b root n. Remember, this Z bracket n is the set of all things in the form a plus b root n, where a and b are integers, right, equal to a squared minus n b squared. So this is a multiplicative norm. On Z bracket square root of n. Okay, so remember, here's the two properties that we need to verify. So for our proof, so we first need to show that n of a plus b root n equals 0 if and only if both a and b are equal to 0. So, so suppose that the norm is equal to 0, which means suppose that a squared minus nb squared is equal to 0. Now, if b is not equal to 0, might suppose that. So oh, right. Yeah, so if this is equal to 0 and b is not equal to 0, then of course a can't be 0 either, right? So if b is not equal to 0, then a is not equal to 0, and what we have is a squared equals n times b squared. Now, every prime factor of a squared, right? So if you imagine a squared, write it out as a product of primes, then every one of the prime factors is going to be even. However, on this side, because we assume that n is square free, this is going to have at least one odd prime factor, right? So on the left-hand side, all even prime factors. Right-hand side, we've got at least one odd. So note that a squared has all, let's say, note that the prime factors, factors of a squared have even powers, while the prime, while there is at least one prime factor of n b squared with an odd power. All right, so what does that tell us then? That tells us that we can't, that b has to equal 0, which then forces a equal to 0. All right, so this can't happen. Let's call that a contradiction. Therefore, well, I guess I start off with b. Therefore, b equals 0. And so if we have b equal to 0 and a squared equals 0, that forces a equal to 0. Therefore, b equals 0, which implies that a equals 0. So if the norm of a plus b root n equals 0, we have that a plus b root n equals 0. And then for the reverse, of course, with the norm as defined, the norm of 0 is equal to 0. Right, so clearly, n of 0 equals 0. Okay, so now we need to show the multiplicative property, and it's really just a matter of cranking things out. So, so here we go. So now, the norm of a plus b root n times c plus d root n, that's equal to, yeah, okay, so I'm just going to multiply this mess out. So this is going to be n of AC plus AD plus BCN, AD plus BC root n, plus we'll have BDN. Oh, and I guess I should have brought that piece over there. Sorry, so this is going to be AC plus BDN squared minus n times AD plus BC squared. Yeah. Okay, and then, and just have to FOIL everything out and see what happens here. So this is an A squared C squared plus 2 ACBDN plus B squared D squared N squared minus N times AD, or A squared D squared plus 2AB, AD BC plus B squared C squared. That's all times N. And so let's see now what happens here. Well, this is going to cancel with that. And so then, does anything else cancel? B squared, D squared? No, that's it. So this is equal to A squared, C squared plus B squared, D squared, N squared minus NA squared D squared minus NB squared C squared. Okay, now if you take what? Let's make sure. A squared N B squared C squared. And so, so if you factor this, this is A minus B. Well, I said it. A squared B squared N. Well, I guess I wrote it the other way. A N B squared times, so you got to factor this, C squared minus N D squared, right? So you can unravel this and verify that this is equal to this, and then this is the norm of A plus B root N times norm of C plus D root N. All right, so that's the end of the proof right now. So we know we've got a multiplicative norm defined as given in the statement, right? A squared minus NB squared. So now, and the key to this proof, right, or at least one of the important parts, right? To get property one, we absolutely had to have square free. And so from now on, so I just want to kind of come out and say this, unless otherwise noted, we assume n is square free, all right, and not equal to 1, right? All right. That's weird. My voice is starting to crack. Maybe my voice is finally changing. Okay, so now, so now I want to choose an element. So let's choose A plus B root n in Z bracket root n. And suppose that when we apply the norm, right, so the norm of A plus B root n is equal to plus or minus 1. Then I'm going to look at, all right, so let's say then 1 over A plus B root n. All right, so that's equal to, so now I need to conjugate it. All right, so before I say equal, so let's do the conjugate here. A minus B root n over A minus B root n. That's equal to A minus B root n over A squared minus B, well, how do I write it? NB squared. Which is equal to A, well, plus or minus right? Because we know that that right down there, that's the norm, right? And we know that that's plus or minus 1. So that gives us plus or minus a minus b root n, which is in z bracket root n. So what just happened? What that tells us is that the inverse of a plus b root n lives inside z bracket root n. In other words, this element right here is a unit. So the only time that we can have the norm, or the absolute value of the norm, equal to 1 is when we plug the unit in the first place. In other words, I guess that's property C of theorem 47.1 holds. We can say thus, theorem 47.1c is applicable which means what? So in z bracket x, sorry, not z bracket x, z bracket root n, if the absolute value of the norm of a plus b root n is prime, then a plus b root n is an irreducible. Okay, so now we have a way when we're working in, right, assuming that n is square free, not equal to 1, right, when we're working in z bracket root n, we have this mechanism that allows us to detect irreducibles. So let me just do one example. How are we doing? Yeah, today's going to be a short lecture. Yeah, okay, let's put it right over here. I'm just going to do one example and call it a day, and then we'll continue with this in the next lecture. So the example in z bracket root 3. If we look at the norm of the element 2 minus 3 root 3, okay, so that's going to be 4, 4, do I even know how to do this? Wait, did I want minus? Oh no, sorry. Plus there, 2, I thought something looked weird. 2 plus 3 root 3, that's equal to 4 minus 9 times 3, which is equal to 4 minus 27, which equals minus 23. That's a prime. What's wrong with me? 4 minus, yeah, okay. So by, well, since, okay, so now we can just say, so it follows that 2 plus 3 root 3 is an irreducible of z bracket square root of 3. Okay, yeah, that's actually a good place to leave off, and then we're going to have a fairly lengthy example coming up. Okay, so we will see you next time.